Alright, we're going to start talking about some concurrent lines, points of concurrency within triangles. And so when we have three or more lines that intersect one point, they are called concurrent. So they have to cross at one spot. The point that they intersect is the point of concurrency. And so triangles are going to have four different sets of points that are concurrent, and the first one deals with perpendicular bisectors. So the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the four vertices. And that's going to have a special name in a minute, but remember, equidistant means same distance. And the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. And again, that's going to look unique and have a special name in a moment as well. So equidistant from the vertices and equidistant from the sides are going to look a little different as we start to sketch them out. So the point of concurrency of the bisectors, the one from the vertices, is called the circumcenter. And the reason that it's called a circumcenter is because we can circumscribe a circle about a triangle. So here's the circle, it goes all the way around, and it just touches the triangle at its four vertices. We talk about circumnavigating the globe, going all the way around. So it goes all the way around the outside of the circle. And so for our example here, if we wanted to find the point where we can circumscribe that circle about triangle XYZ, well, if I get the two perpendicular bisectors, and if I go from the horizontal side and then the vertical side, it's pretty easy to get the bisectors. They're going to cross right here at this point, and that becomes my circumcenter. And so at the point 2, 3, that will be the center of my circle that can go around that triangle. If I wanted to find the radius of that circle, I'd have to use my distance formula to find that distance. Okay. So if we start looking at the angle bisectors, so the point of concurrency of the angle bisector is called the incenter. And then what we can do is we can put a circle inscribed inside a triangle. And so the difference is on the circumcenter, it was on the vertices. This one is on the sides, and it just touches the insides of the triangle. So if I bisect the angles, this will just touch the sides as I go through it. So here's an example. A city planner wants to locate a fountain equidistant from three straight roads that enclose a park. Explain how they can find it. So what we're looking for is somewhere where I can put a circle inside this triangle. And so it's the same process as up here. I need to figure out the angle bisectors. So if I bisect the angles, then the point that they cross, that incenter, will allow me to sketch a circle inside that. That's the same distance from all the roads in this case. Again, that's called the incenter. We have a couple more as we start to deal with it. So if we take the medians of a triangle, those are concurrent at a point, and again, a median goes from a vertex to the midpoint of the opposite side. So here are three medians crossing at one point, and that point is called the centroid. So the medians of a triangle are concurrent at a point 2/3 the distance from each side. Now this is a little bit tricky, so we want to make sure that we do this the right way. So if I look at this, from D to C is 2/3 the distance. From E to C is 2/3, and from F to C is 2/3. So the key is that the 2/3 starts with the vertex and goes to the centroid. It doesn't start with the midpoint. And so if we set that up carefully, then we'll be able to solve these pretty easily. And so down here I have that GE is 24, so all the way across, GE is 24. I want to find GC. Well, E to C is 2/3, and C to G is 1/3 of the whole thing. So 1/3 of the whole thing is going to be 8, because 1/3 of 24 is 8. If I wanted the whole thing of CE, I would take 2/3 of GE, and that's 16. And again, both of those, 16 and 8, are going to make the whole thing, which is 24. Our last one is the altitudes. And so if I take an altitude, sometimes called a height of a triangle, and we got to be a little bit careful because there are three altitudes that we can have here. One is inside, one is a leg of a right triangle, and one falls outside. These are concurrent. And so the lines that contain the altitudes, they cross at one point as we go through this. They are called the orthocenter. They don't have as nice of a property as the incenter or circumcenter, but they are concurrent. And we can see here that my altitudes, these all fall inside my triangle. They cross right here at this point called the orthocenter. And so if I look at this example here, JT is in an altitude, a median, neither or both. Well, it's an altitude because it's a right angle, right? So it's the height of my triangle. And it's also a median because it intersects the vertex and a midpoint. So it has to be both as it crosses through those. Okay, so we're using our definitions of altitude and midpoint as we go through it. And so we'll down the road fill out a chart to help us kind of organize this, but that's it for right now.